Velocity is the rate of change of the position of an object, equivalent to a specification of his speed and direction of motion, for example 60 km/h to the north. Velocity is an important concept in kinematics, the branch of classical mechanics which describes the motion of bodies. Velocity is a vector physical quantity. Both magnitude and direction are required to define it. The scalar absolute value of velocity is called speed, a quantity that is measured in meters per second in the SI system. For example, 5 meters per second is a scalar, whereas 5 meters per second east is a vector. If there is a change in speed, direction, or both, then the object has a changing velocity and is said to be undergoing an acceleration. Constant velocity versus acceleration. To have a constant velocity, an object must have a constant speed and a constant direction. Constant direction constrains the object to motion in a straight path. Thus, a constant velocity means motion in a straight line at a constant speed. For example, a car moving at a constant 20 km/h in a circular path has a constant speed, but does not have a constant velocity because its direction changes. Hence, the car is considered to be undergoing an acceleration. Distinction between speed and velocity. Speed describes only how fast an object is moving, whereas velocity gives both how fast and in what direction the object is moving. If a car is said to travel at 60 km/h, its speed has been specified. However, if the car is said to move at 60 km/h to the north, its velocity has now been specified. The big difference can be noticed when we consider movement around a circle. When something moves in a circle and returns to its starting point, its average velocity is 0, but its average speed is found by dividing the circumference of the circle by the time taken to move around the circle. This is because the average velocity is calculated by only considering the displacement between the starting and the end points, while the average speed considers only the total distance traveled. Equation of motion. Velocity is defined as the rate of change of position with respect to time, that is, where v is velocity and x is the displacement vector. This will give the instantaneous velocity of a particle, or object, at any particular time t. Although the concept of an instantaneous velocity might at first seem counterintuitive, it is best considered as the velocity that the object would continue to travel at if it stopped accelerating at that moment. Although velocity is defined as the rate of change of position, it is more common to start with an expression for an object's acceleration and from there obtain an expression for velocity, which can be done by evaluating, which comes from the definition of acceleration. Sometimes it is easier, or even necessary, to work with the average velocity of an object, that is to say the constant velocity, that would provide the same resultant displacement as a variable velocity, v, t, over some time period it. Average velocity can be calculated as the average velocity is always less than or equal to the average speed of an object. This can be seen by realizing that while distance is always strictly increasing, displacement can increase or decrease in magnitude as well as change direction. In terms of a displacement time graph, the velocity can be thought of as the gradient of the tangent line to the curve at any point, and the average velocity is the gradient of the chord line between 2 points with t-coordinates equal to the boundaries of the time period for the average velocity. Constant acceleration. In the special case of constant acceleration, velocity can be studied using the Swavat equations. By considering it as being equal to some arbitrary constant vector, it is trivial to show that with v as the velocity at time t and u as the velocity at time t equals 0. By combining this equation with the Swavat equation x equals ut plus at 2/2, it is possible to relate the displacement and the average velocity by. It is also possible to derive an expression for the velocity independent of time, known as the Torricelli equation, as follows. Where v equals v etc. The above equations are valid for both Newtonian mechanics and special relativity. Where Newtonian mechanics and special relativity differ is in how different observers would describe the same situation. In particular, in Newtonian mechanics, all observers agree on the value of t and the transformation rules for position create a situation in which all non-accelerating observers would describe the acceleration of an object with the same values. Neither is true for special relativity. In other words, only relative velocity can be calculated. Quantities that are dependent on velocity, the kinetic energy of a moving object is dependent on its velocity by the equation, where ek is the kinetic energy and m is the mass. Kinetic energy is a scalar quantity as it depends on the square of the velocity, however a related quantity, momentum, is a vector and defined by. In special relativity, the dimensionless Lorentz factor appears frequently, and is given by where I³ is the Lorentz factor and c is the speed of light. Escape velocity is the minimum speed a ballistic object needs to escape from a massive body like the Earth. It represents the kinetic energy that, when added to the object's gravitational potential energy, is greater than or equal to 0. The general formula for the escape velocity of an object at a distance r from the center of a planet with mass m is where g is the gravitational constant. The escape velocity from Earth's surface is about 11 100 meters per second. Relative velocity. Relative velocity is a measurement of velocity between two objects as determined in a single coordinate system. Relative velocity is fundamental in both classical and modern physics, since many systems in physics deal with the relative motion of two or more particles. In Newtonian mechanics, the relative velocity is independent of the chosen inertial reference frame. This is not the case anymore with special relativity in which velocities depend on the choice of reference frame. If an object A is moving with velocity vector v and an object B with velocity vector w, then the velocity of object A relative to object B is defined as the difference of the two velocity vectors. Similarly, the relative velocity of object B moving with velocity w, relative to object A moving with velocity v is. Usually the inertial frame is chosen in which the latter of the two mentioned objects is in rest. Scalar velocities. In the one-dimensional case, the velocities are scalars and the equation is either, if the two objects are moving in opposite directions, or, if the two objects are moving in the same direction. Polar coordinates. In polar coordinates, a two-dimensional velocity is described by a radial velocity, defined as the component of velocity away from or toward the origin, and an angular velocity, which is the rate of rotation about the origin. The radial and angular velocities can be derived from the Cartesian velocity and displacement vectors by decomposing the velocity vector into radial and transverse components. The transverse velocity is the component of velocity along a circle centered at the origin. Where is the transverse velocity, is the radial velocity. The magnitude of the radial velocity is the dot product of the velocity vector and the unit vector and the direction of the displacement. Where is displacement. The magnitude of the transverse velocity is that of the cross product of the unit vector and the direction of the displacement and the velocity vector. It is also the product of the angular speed and the magnitude of the displacement. Such that angular momentum in scalar form is the mass times the distance to the origin times the transverse velocity, or equivalently, the mass times the distance squared times the angular speed. The sign convention for angular momentum is the same as that for angular velocity. Where is mass? The expression is known as moment of inertia. If forces are in the radial direction only with an inverse square dependence, as in the case of a gravitational orbit, angular momentum is constant, and transverse speed is inversely proportional to the distance, angular speed is inversely proportional to the distance squared, and the rate at which area is swept out is constant. These relations are known as Kepler's laws of planetary motion. See also. Notes. References. Robert Resnick and Jill Walker, Fundamentals of Physics, Wiley. 7 sub-edition. ISBN 0-471-23231-9. External links, physicsclassroom.com, Speed and Velocity, Introduction to Mechanisms.